My name is Carol Serdar-Tepper, and I'm with the Quimper Geological Society. Thank you for coming today on a blustery Saturday, March 8th, 2025. We have a really great speaker lined up today, and it looks like many of you read the newspaper and have joined us today. Welcome. If you are not a member, there's no membership fee. Just get onto the website, Quimper Geological Society, and sign up, and we send you an email 10 days before the event, and then 2 days before the event. And then we have a website that's updated frequently. So check things out frequently at the website, quimpergeology.org. We would like to give thanks to the Coast Salish peoples for being great stewards of the land. And we hope that these presentations help people understand why it's important to be great stewards of the land. We have two more for the 24-25 lecture season. We have two more presentations coming up. April 12th will be Dan Muse, and it will be Zoom only. Unfortunately, he had a family, something that came up and is unable to make it to Washington. So please join us for Zoom. There will be a link on our website, but if you're a member, you will get a newsletter that has the link on it. And then May 3rd, we're having Leah Tucker and another undergraduate student will be doing a presentation as well. And now I'd like to introduce Ralph Dawes, who will do the introduction. Thank you.
Ralph, and I've only just met Daniel Coe, Dan, today, but I've seen his graphics and his maps online and at meetings, and I've been very impressed for a while. So what I've picked up about Dan, well, first of all, you can give him several titles for the work he does, such as graphic artist, graphic designer, but cartographer is a key one. And to me, looking at what cartographers do, it's an art and a science combined. To make maps is what cartographers do. So some of the posters aren't necessarily based maps that Dan's been involved in, but a lot of it is. And then recently, and by the way, as a geologist, I mean, maps, that's like if you're studying Shakespeare, having the sonnets, you need the maps, or you're going to make maps. And then with Lidar technology coming out in the last 20 or so years, which Dan is very good at taking advantage of and turning into maps that you can't see when you just go to the Washington Lidar portal, there's amazing things to see and learn from his work. So, and I know people have been taking advantage of the free posters from the Department of Natural Resources and so on, and other handouts back there, which is great. Thank you, Dan, and the state of Washington. Anyway, so one thing I picked up was that I think you have an art background in your education, along with geography. So art and science, plus I heard you say that you have some geoscientists in your family. So yeah, so interdisciplinary, straddling that, breaking down those borders and producing all this great work, among other things. So without much further ado, here's Dan Coe to talk about the glacial landforms of the Puget Sound area. And thank you, Dan.
To see a full house here in the room today. So, I'm really excited to be here this afternoon. Today we're going to take a whirlwind tour of Washington using historical and contemporary maps from 3 different glacial realms: the Ice Age floods and glaciation on the east side of the Cascades, Alpine glaciation in the Cascade Range and Olympic Mountains, and finally, Ice Age glaciation here in the Puget lowland. As you can see, I managed to get a 15,000-year-old photo of Washington. It's pretty hard to come by, but feedback there. Actually, this is a photo of the Patagonian ice field in Argentina. I thought I made a pretty good analog for what Washington might have looked like 15,000 years ago or so. Before I get to the maps, though, I thought I'd give you a little background on the Washington Geological Survey and the Washington Department of Natural Resources, where I work. So the Washington Geological Survey is just one small division within the larger DNR agency. We currently have about 65 employees. And here's the survey's mission statement. I'll let you read that over. But I would also say in the process of fulfilling this mission, we also tell the geologic story of the state. These are a few of the main programs at the survey. We've got geologic mapping and hazards, regulation and resources, education and outreach. We also collect Lidar for the state, which I'm going to discuss here in just a minute. So as Ralph said, I'm the graphics editor for the survey, so I do a lot of basically visual work, but the core of what I do is as a cartographer. So, I'm one of a handful of people who are not geologists that work at the survey. Again, my background's in art and geography, but I have a particular interest in maps. And as Ralph said, walking that line between art and science is something that I love to do. So much of my work supports the science teams in our division. These are a few of the visual products, including several maps that we produce. Many of our maps use LiDAR data to help interpret the geology of our state, and I'm going to be showing quite a bit of that here tonight. So if you're not familiar with LiDAR, it stands for light detection and ranging, or light radar, depending on who you ask. And airborne LiDAR is collected from a sensor in an airplane, flies over the land, shoots a bunch of lasers at the ground. That gets reflected back up into a sensor in the airplane, which records the distance of that reflected light. So it's kind of like a laser rangefinder that you might point at a wall, but multiply that by about 1 billion. Those measurements create a very dense data set called a point cloud, which is made up of those individual measurements. So you can see that example. This is Beacon Rock in the Columbia Gorge. Let's get a little better view of that. So that is an image that is made up of millions of little tiny laser data points. So it's three-dimensional data. We can take that and we can make different kinds of three-dimensional models out of it. The one shown here is called a top surface model. It's kind of like if you just shrink wrapped the entire Earth with trees and buildings and everything underneath it. This kind of model, it includes trees and buildings, but then we can also switch over to what's called a bare Earth model. It's also called a digital terrain model. And that's where you can basically digitally remove all the vegetation and buildings, leaving only the bare ground. So, here in Western Washington, if you're a geologist, geologists don't tend to like trees very much because you can't see the ground. So this kind of technology is kind of a revelation. And, for geologic purposes, again, we're mostly using that bare Earth model because we can see the ground. So this data can be displayed a number of different ways. These are just a few of them. I'm sorry, I'm really sorry about that. I'm like doing 2 computers at once here. So let's go back. Sorry about that. So this is the point cloud with all those little laser measurements. This is the shrink wrapped version that I talked about. And then this is that bare Earth. So peel all those trees away. And these are kind of some different ways that you can display this data. So that orange image, it's displaying elevation with color. So the white is lower elevations, the orange is higher elevations. You can make topo lines, like a topographic map out of that. You can do what's called shaded relief, where it's sort of lit up from, technological issues, sorry about that, where it's kind of lit from an artificial angle. You can measure slope in this black and white image, and you can also measure aspect, and that just shows basically what direction the land's facing. So you can do a lot of different things with it. Again, the reason it's so useful for geoscientists is because it offers a truly unprecedented view of the Earth's surface. So things like landslides, faults, glaciers, volcanic eruptions, floods, erosion, they've all left their fingerprints on the landscape. So it's a great tool for communicating geology and natural hazards with maps as well. So I got my start working with LiDAR data about 15 years ago while working for the Oregon Department of Geology and Mineral Industries, known as DOGAMI. I was experimenting with some new LiDAR data of the Willamette Valley that we had just received one day. And as I was adjusting the color and elevation values, all of a sudden this really interesting image appeared on my screen. That's the image you see here. This is the Willamette River in floodplain. And there's kind of the fuller view of it. So my coworker at the time, he was a fluvial geomorphologist, so somebody who studies rivers, and he looked over and said, "Wow, that's amazing. We should do something with that." I showed it to some other people. They thought it was really interesting. But as a scientific organization, we hadn't really published sort of semi-abstract art up until that point. So nothing really became of it at the time. But a few months after that, I saw this mapping competition somewhere. And it was for the inaugural Atlas of Design, which was a collection of sort of well-designed and interesting maps from around the world. So to my great surprise, the Willamette River image got accepted into the Atlas of Design. So Dogami thought they should probably publish it somehow. And they published it as a poster. The nice thing about this, it actually does tell a geologic story. In the Willamette Valley, there's a lot of Missoula flood sediments. So that's what this river is basically winding through. And we'll come back to that story a little bit later on. But after that, though, after they published it, Dogami also did something that influenced my mapping career. They announced that all their publications were in the public domain, which means anybody could use them for anything. And so they basically did. So this kind of opened the floodgates, so to speak, on how this image was used. And it made me realize that I might be onto something here. People were, really interested not only in the story of the Missoula floods that this image told, but also the somewhat whimsical and abstract aesthetic that the river image evoked. So again, that intersection of art and science is something that cartographers like myself absolutely love. And this was a great example of how that intersection could really draw people into a subject that maybe a standalone photo or story couldn't do. One other really added benefit, though, to that story of public domain is now you can get it on tights, you can get curtains, all sorts of fun things. These are all images that I stole from the internet, so they are real. All right. Okay, so as a cartographer, I feel lucky every day to live in such a topographically interesting state. Here we are in Port Townsend today. So as you probably know, glaciers have shaped basically almost all of our state in some way. Whether it's from direct contact with glacial ice, or the catastrophic effects of ice age floods, or to the wind-blown glacial sediment of the Palouse. Glaciers have affected much of Washington. Okay, so let's start by heading eastward to discuss the channeled scablands and the ice age floods. So again, tonight I'm gonna show a lot of different maps from going back about a century to modern day. I just want to point out, there's a lot of geologists and cartographers and people that have come before me that have made all this amazing stuff. So I'm going to try to show as many, interesting Pacific Northwest maps as I can. There's a lot that I'm not showing tonight that are also really important and great. So just bear with me here. So this is a map from, I believe, the late 90s. Yeah, late 90s from the U.S. Forest Service. And it's kind of hard to see. This is kind of a faded out version of it, but it did a really good job of mapping the paths of the Missoula floods and the channeled scablands. So the Ice Age floods, also known as the Missoula floods, were cataclysmic glacial outburst floods that flowed across the Pacific Northwest during the last Ice Age. Some industrious person at some point took that map, digitized, basically traced all those little features so it could bring it into a digital system. We can make more maps out of it. So this is a great example of one of the maps that was made by Eastern Washington University a little while back. You can see those flood paths and channels a little bit better. So in 2016, we used that same data to make this poster of the Ice Age Floods National Geologic Trail for Earth Science Week. And shortly after that, we also released an interactive narrative that used that map along with some other images, video, and text to tell the story of the Ice Age floods in Washington. So these are a few of the graphics from that narrative. So if you're not familiar with the Missoula floods or the Ice Age floods, the person up there in the corner is J. Harlan Bretz. He was a major figure in the Ice Age flood story, to say the least. Bretz was a geologist who theorized that the channeled scablands of Washington were created by some sort of catastrophic floods. And for many decades, his ideas were met with skepticism from the general geological community. But over time, his ideas became more widely accepted as more and more evidence came to light. So for that interactive narrative, we basically used that poster for Earth Science Week. We used that map as our template, and we made a sequential series that showed kind of an animated, self-guided version of the floods. So between 15,000 and 12,000 years ago, a lobe of the Cordilleran ice sheet blocked the Clark Fork River near Lake Pend Oreille in modern-day Idaho. I'm going to get my laser pointer out just to point out a few of these things.
The remote also has one.
Little remote. This one?
Yeah, that was it.
When I tried it before, I turned the screen off, so I'm probably pushing the wrong button. Oh, there we go. Okay, thank you. Okay, so there's ice dam right up there. And that ice dam created this enormous lake known as Glacial Lake Missoula. You can see back here. So just for context, make it a little easier to see, there's Washington, kind of highlighted. Sorry, there's Washington. So there's evidence that ice dam holding back the lake failed repeatedly, releasing periodic glacial outburst floods across the plateau. Those floods scoured everything in their path, carving broad, deep channels into the landscape, known as the channeled scablands. And then the waters flowed into the Columbia River Gorge, into Oregon's Willamette Valley, before eventually draining into the ocean. So there's evidence of Glacial Lake Missoula. If you've ever been in Missoula, Montana, there's a couple mountains right above town where you can see these lines, these sort of horizontal lines on the landscape. This photo is from 1904. I thought it did a pretty good job of showing those lake strand lines. Those are basically the lake levels of where that Ice Age lake was. Not too far from there in Montana is another major site for the Ice Age floods evidence called Camas Prairie. And this is where there's giant ripple marks that testify to the large amount of water that once flowed through this region. And this is a map of Camas Prairie, the ripples by J. Harlan Bretz, who I mentioned earlier. And it was published back in 1942. And that's an aerial photo from a few years ago, just looking down at the ripples. And you can see, even in that photo, you can really see them quite clearly. But with Lidar, you can kind of change the lighting angle and make things really pop out. So it gives you a super, super detailed view of those ripples. And the really neat thing is if you superimpose Bretz's map over top, it matches up really well. He did a good job. There's a zoomed in view.
Those right on 990.
North a ways from I-90, I think. So this is Bretz's 1959 channeled scabland publication map showing the scablands and lusk-covered areas in eastern Washington. We'll zoom in a little bit here. And this is the Cheney-Palouse scabland track, kind of east of Ritzville, if you're familiar with that area. And this is a photo of that same area. And you can see those channels show up really well in a photo. We also made a map of it a few years ago just using elevation data, and they really pop out really well. More recently, though, Lidar was collected for this area, so I made an image of just the northwestern portion of the image up here. So we're going to zoom in there. And there's the photo showing those scablands really clearly, but then here's the Lidar view. It does a really great job of contrasting those sort of eroded landscapes with the sort of smoother, untouched lush hills that you see surrounding them. All right, so this is a 1932 map of Grand Coulee, also by Bretz, and it shows topographic features as well as the direction of the glacial currents. It's kind of hard to see, but there's a lot of little arrows pointing up there where he theorized that the water was flowing. In the northern part of this image is the Columbia River, Steamboat Rock, if you've ever been in this part of Washington. And then as you go further south, you get to Dry Falls, which is a huge series of cliffs carved by the Ice Age floodwaters. And then as we move down toward the middle of the map is Dry Falls. I'm sorry, I'm skipping over here. It's kind of like patting my head and rubbing my tummy here, so bear with me. So as you move further south, this is the lower Grand Coulee. So this is Dry Falls, and as water flowed through, it opened up out onto the Quincy Basin here, which is kind of a larger, more open, flat area. So we're going to travel that route. This is a view over Steamboat Rock, kind of in the northern part of the Grand Coulee, over Banks Lake. Back when Brett's made that map, he wasn't showing the lake there because it wasn't there yet. So we're going to move a little further south. This is Dry Falls. This is the view from the visitor center there. The thing that blows my mind about Dry Falls is it's a landscape that's so big, it's really hard to wrap your head around the full scope of it. And up until recently, we didn't have LiDAR for this region, but last year we finally got some. So here's the top-down view. This is Banks Lake up here, and these are the cliffs all along here. So the water flowed in from the north. And just to give you an idea of how big this is, that's about 3.5 miles wide. So just a really massive area. For context, that's about 4 times the width of the whole Niagara Falls waterfall complex. And the reason I bring that up is because Brett's made that comparison too. So this is Niagara Falls, same scale, and this is Dry Falls. So if you've ever been to Niagara in New York or Canada, it just dwarfs it. So this is just kind of an air photo of Dry Falls. It does a pretty good job of kind of encompassing the whole thing, but you don't really get the feeling of how big it is. When you add in LiDAR, though, it just pops right out. And the nice thing about using that is it's 3-dimensional, so you can look at this from any angle that we want to look at it. We're in the process of making a map out of it, so let's zoom in a little. It's just amazingly detailed. Okay, so as those floodwaters flowed south from Dry Falls, they flowed out. This is Soap Lake out onto this plain. This is another Brett's map that shows all those different directions of where the water likely flowed. So we're going to switch over, change our angle. Is that because of this one? So this is a photo of the Quincy Basin. Let's rotate it just to get a better maximizing our space here. So north is this way. The water's flowed out. If you've ever been to Moses Lake, it's right there. This is Potholes Reservoir right there, to give you an idea. Each one of those crop circles is about half mile across. So this is about a 40-mile wide image. So let's blend that with a little bit of LiDAR to start to see those channels. They're huge. It's amazing. 40 miles wide. So if you look over here, this is Drumheller channels, and you can see there's a lot more intricate channels over there. So let's transition over to that area. Here's a view from the air looking south over Drumheller. Classic channeled scablands landscape. And here's an air photo. This one's about 10 miles wide. But with LiDAR, ooh, looks good. Again, it really contrasts the flood-affected areas and the unaffected areas. Okay, moving northwest onto the Waterville Plateau, we find the Withrow Moraine, marking the extent of the Okanagan ice lobe of the Cordilleran ice sheet. And this is an aerial photo of Upper Moses Coulee, Jameson Lake, and the Withrow Moraine. And here's a LiDAR view of it. Just want to point out kind of the textural differences. You can see these glacial lineations here, these lines. You can see this sort of moraine-like hummocky texture. And then you get down here, everything's smooth. That's because that's about where the edge of that glacial ice got to. So we're going to look a little closer at this image. Right up here is a spot we're going to zoom into. So Ralph got a hold of me last year and sent me one of his posters about glaciotectonic landforms on the Waterville Plateau. Specifically, one's called hill hole pairs. So let's switch over to LiDAR and we'll get a little better view. So hill hole pairs are defined by landforms that have been excavated and transported by glacial ice. So in this image, we can actually see two hills that are likely part of that type of feature. These ones right here. Now, if you look just to the north, you can see shapes that look very much like those. Let's just move those up there. Put them back. They fit pretty well. This one might have gotten squished a little, but almost like a puzzle piece, putting them back in there. Just thought that was pretty neat. All right. Moving just a little bit southward from there along the Columbia River, there are giant current ripples at West Bar. And these boggle my mind every time I see them. So you can see these ripples in the background. These are about 25 or 30 feet tall. And they were created by Ice Age floodwaters flowing down the Columbia River corridor. Here's an air view. Not terribly exciting to look at, but this is Trinidad, Washington, if you've ever been over that way. I think Quincy's over here. But again, with LiDAR, get a little bit of lighting on there. We'll zoom in and really see the nature of those features. This is a little road for geographic context. And here's a view looking south. This is West Bar and the Columbia flowing southward. Okay, so remember, if we follow that Columbia River corridor along the flood routes, you can see that water's filled up the Willamette Valley all the way down to Eugene, which is pretty incredible. So let's switch over to a map showing those features. So this is a map from the USGS from about 20 years ago that does a really good job of showing flood inundation in blue over here. And it also shows the locations of ice-rafted erratics and glacial Missoula flood sediments. So to give you an idea of what an ice-rafted erratic is, here's a picture of a pretty well-known one in Oregon. This is at about 300 feet of elevation in the Willamette Valley. This is kind of a roadside state park there. And one of the reasons we know how much the Willamette Valley got filled up with floodwaters is based on where the locations of these are, where they were found. So they're found up to 400 feet in elevation. And this particular one, I believe, is made up of argillite and came from Canada originally. And that's the location right over there. Okay, remember this one? That's where it goes. Sorry, this one. That's where that was, right there. So you can kind of get that geographic connection between the Missoula floods and that Willamette River image. Okay, so Alpine glaciation has also had a profound impact on the landscape of Washington. This is an early morning view of the glaciers on Mount Rainier, seen from White Pass. There's a lot of, my back, okay. There's a lot of really great maps of Mount Rainier out there going back, showing the glaciers and everything many years. This one's one of my favorites though. This is basically a map painting by geologist, artist, cartographer, mountaineer extraordinaire, D. Molinar. And if you don't know about D, look him up. Fascinating human being. I've got a couple more images from him in this presentation, but this is actually an 1896 USGS map of Tahoma's glaciers. Does a really good job of displaying them. We go to modern day. Here's the current day view, the photo. But again, if we want to get a really good look at those glaciers, we can switch to LiDAR and show them in blue, much like that 1896 map. You can also do things like compare glacial extents over time. This is comparing 1924 to 2008. Mount Rainier was actually reflown with new LiDAR data last year, so it's going to offer new opportunities for research in alpine glacial change. I'm sure it's already being done. And remember, this is three-dimensional data, so we can turn it on its side and get perspective views of that information. This is in Mount Rainier. This is Mount Baker up north in Whatcom County. So I take a lot of inspiration for those types of maps and images from a lot of these older bird's eye view maps, one of which you can see here of New Tacoma and Mount Rainier. Here's another one I added in today. Whoops. Actually, I don't have that in there, so we'll go kind of to a modern day view. This is similarly a composite imagery map of USGS Lahar hazard zones at Ording in Pierce County. And, you know, if Mount Rainier were to heat up, the glaciers could rapidly melt, creating volcanic debris flows known as lahars, which could flow into downslope communities. So this community is actually built on top of a 30-foot thick lahar deposit from 600 years ago. So this is a very real potential hazard for this area. All right, so speaking of volcanic hazards, you know, 45 years ago, Mount St. Helens reminded us that volcanoes can be dangerous. This is a pre-1980 photo of that glorious glacier-capped peak of St. Helens. And then, of course, this happened. And we can kind of show that change in the glaciers with these USGS topographic maps. You can see the glacial extents in blue. So between 2004 and 2008, a new lava dome actually grew inside the crater of Mount St. Helens. And the USGS actually tracked that with Lidar data. That also coincided with major growth and advancement of the newly formed crater glacier, which you can see in blue here. So we're going to go through a sequence of images over those few years to see how it grew. So just pick one of these sides and just look at it as I click through. And you can see that growth of the glacier dome actually kind of pushed the glacier, or of the lava dome, pushed the glacier out of the way and down slope. So it kind of merged back in with itself. This is a view I took from 2013, looking down into the lava dome and the glacier. All right, so in 2001, I made a map of Mount St. Helens, and I wanted to create a LiDAR-based perspective view interpretive map of the volcano, since I hadn't really seen that type of map of St. Helens before. In researching ideas for the map, I came across these beautiful 1980 USGS illustrations by D. Molinar, who I mentioned earlier. Here's another one of the before and after. Really great illustrations of how the mountain changed. So these further inspired my idea for a bird's eye view style map of the volcano. And this was the eventual angle that we picked. And then there's the map, which we published in 2022. There might still be a few back there, I'm not sure. So this map actually showed 5 different ways the landscape of Mount St. Helens has changed in the past several decades. Here's a zoomed in view. One of those ways is that growth of the crater glacier. And you can see it's grown even more, poked a little further down slope, kind of bucking the trend of melting glaciers in most of the world. All right, this is one of my favorites. This is a map painting of glaciated peaks in the North Cascades by Heinrich Moran, who made several of these for the National Park Service back in the 1980s. So these types of perspective view maps are really inspiring to me. And last year, I started wanting to do more of those types of maps. So I started making a couple maps of the Enchantment Range, or the Stewart Range, I should say, in the Cascades. So this is kind of the pre-dawn view. This is just elevation data. This is not almost looks like a photo flying over, but it's just data. And made a little map out of it, added a little Alpine glow, made a little peak locator. So if we go just north of there, we find Lake Chelan. And you know, Lake Chelan had glaciers carving it from both ends during the last ice age, and it left behind Washington's deepest lake. So this is a depth profile from a 1987 Washington Department of Ecology report. So we kind of took this idea and made a new version of it for a map we were making. And we wanted kind of a yardstick that people could recognize. So if you look closely over here, you can see Lake Chelan is about 2.5 Space Needles deep. So, and this is the map that it went on of the lake. All right. Let's switch over into our neck of the woods here. This is a place you're probably all familiar with, the Olympic Peninsula and Olympic National Park. Let's zoom into the center of this image, into Mount Olympus and its glaciated peaks. So the Blue Glacier on Mount Olympus is probably one of the most studied glaciers in the world. You can see we've got comparison images going back to 1899 here. And you can see the drastic change in ice volume from there to here in 2008. So a few years back, we made a map of Mount Olympus, and we wanted to add in just a little hat tip to that. So you zoom in, you can kind of see that approximate 1899 extent drawn in. Back in 2003, I actually got to take a backpacking trip up to the Blue Glacier and Mount Olympus, and I took several photos. This is the terminus of the glacier in 2003. I went back this past year in 2024, so almost over 2 decades later, and I actually couldn't recognize that same viewpoint. It had changed so much in that time period. This is still from 2003, but if you look closely, there's a crack in the cliff face right here. And when I got there this past year, that entire cliff face had in the intervening years collapsed into the valley below. So it was kind of a surreal experience trying to recognize, what I had seen 20 years earlier with what I was seeing then. And it's hard to see here, but the line of the glacier was basically up here in 2003. So just a huge change. And that rock that was kind of poking out of the ice is like over here. So not only did the length of it change, but it also sunk quite a bit as well. All right, a map some of you may be familiar with by Tabor and Katie from 1978. So let's zoom in. Mount Olympus isn't the only place that was affected by glaciers in the Olympic Peninsula. So this is the Quinault Valley. You can see Quinault Lake up here. I'm going to highlight, there's some little dotted lines here. We're going to highlight those. And those are all mapped glacial moraines. So that's telling us that there were glaciers down here at one point in time. So let's switch over to a really colorful Lidar view and turn those off. So this is just with elevation data. You can actually see those moraines are a little bit darker there. Lake Quinault's a moraine dammed lake. You can see the moraine right there. You can see them all the way down here. It's really fascinating. So I thought this kind of looked like a Piedmont glacier that I had seen in some images of Antarctica. So I just clipped that image of that glacier in Antarctica and just plopped it over top of here. And it fit pretty well. Thought that was pretty neat. And of course, we can make it bigger. Oh, it still fits. But you don't even really need that to see that shape in the landscape. All right, and there's the air photo, which you can't see anything. Okay, so let's start the third section of this presentation, glaciation in the Puget lowlands. So this region was obviously dramatically shaped by the Puget lobe of the Cordilleran ice sheet, which, it created this beautiful watery island speckled landscape that we see today. This is a view from Mount Erie near Anacortes, one of the best views around. So that glacial ice created what was dubbed in this postcard map from 1910 as America's Mediterranean. I don't know if you can read that. Or the American Mediterranean. I don't know if you all agree with that. When it was raining last week, I don't think I agreed with that very much. I think it was for tourism purposes, for sure. So this is a beautiful 1966 rendering of the Puget Ice Lobe by Alan S. Carey of the U.S. Army Corps of Engineers. We'll zoom in a little bit here. So here we are underneath the ice up here. You can kind of see Puget Sound outlined in those dotted lines. So a few years back, we used that idea to create kind of a new generalized rendering of the Puget Lobe based on some more recent southern ice extent data. And we also use this map of the Puget Low Glacial Retreat by Robert Thorson as a guide for sort of multiple iterations of the ice lobe. So here's what that ended up looking like. And we use those two ideas to make a series of really simplified maps to show the various glacial lakes that formed in the Puget Lowland as the Cordilleran ice sheet receded over time. So I'm just going to click through a series sequence that culminates in our modern day Puget Sound. Okay, we can see Glacial Lake Hood, Glacial Lake Nisqually, Glacial Lake Puyallup, Glacial Lake Russell. Keep going. We get to Glacial Lake Bretts. You can see we're almost out of the ice here. And Glacial Lake Bretts overflowed right through here to the strait. And then we have present day Puget Sound. And you know, like Lake Sammamish and Lake Washington over here, these are remnants of those glacial lakes. And I also want to point out that we're probably going to need to revise some of these ice extents and directions based on, you know, some of the recent work by Ralph Hagrud and others. But I thought it did a pretty good job still of kind of showing where those glacial lakes were. And, you know, using LIDAR data, it's really neat because we can actually see evidence of those glacial lakes in different places throughout the Puget Lowland. So this is what you see from the air, but here's a LIDAR view. So there we go. So this is a really large overflow channel that cuts across the land near Shelton. I actually drove across this today coming up here on Highway 101. So you can actually see drumlins, eskers, these little snaky things, kettle lakes, all sorts of different things in this image that tell us that there was a large glacier here in the past. And that area today, this is mostly just filled in with peat today. There's no channel running through there. It's just basically a big bog. This is Highway 101, right through there. So as the glacial ice scraped across the land, it also left fluted ridges, which are also known as drumlins in much of the Puget Lowland. So this is an aerial photo of Lower Hood Canal, and here's a view with LIDAR. So you can really see those glacial lineations across the land, really vivid. This is actually a map of those, oops, there we go. This is a map of those topography-derived glacial flow lines by Thorson as well. So we can actually map where the glacier moved based on those hills. Here's another good example of that. This is Green Mountain and Gold Mountain on the Kitsap Peninsula, kind of the tallest peaks out there. And you can map those flow lines using these arrows. I think this is Bremerton over here for context. Here's one additional map by Thorson. This shows approximate maximum Puget Lobe ice elevations. So we could take this, subtract the modern day landscape from it, and make sort of a simplified ice depth map out of it. And you can see here in Port Townsend, we were under about 4,000 feet of ice many thousands of years ago. Pretty wild. So, you know, the weight of that ice depressed the land underneath it. And as the ice receded and went away, much of that land began to rebound and come back up. And you can actually see evidence of this elevation change in the northern islands of Washington. So this is Cattle Point on San Juan Island. You know, when that glacial ice receded, land came back up. That combined with sort of changing sea levels left behind relic shorelines and wave-cut terraces in many parts of Puget Sound and the San Juan Islands. You can see these wave-cut terraces here, some shorelines. I apologize for the sand dunes flipping everybody off. Probably should have thought about that a little more when I was tracing those out. How rude. But I'm going to show a photo here in a second that's taken from down here looking at these terraces. So you can actually see them just from the ground, those former shorelines. Pretty neat. Okay, so there's one type of glacially related geomorphic feature in the Puget Lowland that's fairly mysterious, and those are the Mima Mounds. And Mima mounds are, areas of patterned ground. They all occur in glacial outwash prairies, at least in the southern Puget lowland. And there's not really a universally accepted theory for how they were created. And before J. Harlan Brett set his sights on the channeled scablands, he was working out the mysteries of the Puget lowland here in this side of Washington. And this is actually a drawing of his from the early 1910s. I guess around, or 1913, published by the Washington Geological Survey. Yay, go Geological Survey. Here's a view from the sky of the mounds. We went out there a couple falls ago and took some photos, and it was just kind of neat with the fog receding over the land. And here's an air view, and then the Lidar. So is it a basketball? Is it chicken skin? I don't know. But you can definitely see there's kind of a flow pattern going on with these. So I don't know. Earthquakes, floods, gophers, aliens, who knows? And this is actually a LiDAR scan of that same area. Pretty fun. But I'm going to connect back to that here in a second, but back to this Puget Lobe map by Alan Carey. We zoom in, sorry, go back here. As you can see, all these westward flowing rivers from the Cascades basically ran into this ice and had to go somewhere. So a lot of them flowed down to the Chehalis River Valley, which at the time was probably closer in size to what the Columbia River is today. So a much larger river system. I just want to note Eatonville right here. You can see where that is. We're going to go to this next photo. This is Ohop Lake, and that's Eatonville right there. So we're looking south. Ohop Lake is actually one of those drainage channels from the water flowing outward there. And, geologists Pat Pringle and Barry Goldstein and others have found evidence of glacial outburst flooding from Glacial Lake Carbon along this valley and the Tanwax Valley, which is right next to it. That also it connects to the story of the Mima Mounds as well. And this is a nice rendering of that flood pathway by DNR's Luis Prado, kind of showing the connection between Glacial Lake Carbon and the location of where the Mima Mounds are all found in these prairies. So we'll go back to the early 1900s. This is another map by Brett of that same area, showing these different channels where water flowed. I just want to point out really quick here, Scatter Creek. The next image is going to have Scatter Creek in it. And this is Scatter Creek flowing through Violet Prairie. This is Interstate 5 right here. Scatter Creek's a really tiny little creek that flows through there, not very big. But when we switch to LiDAR, you can see it was a bigger river back then, just spanning that entire width of that valley. And if you were to zoom in really closely to this image, you can see there's Mima Mounds all over this prairie. So there's some sort of connection there. Not exactly sure what it is, but. That's not the only place where there's these just amazing channels. This is northwest of Olympia along Bingham Creek, which flows into the Satsop River, if you're familiar with that area. This is basically just commercial forest land. You can't really see much. But with LiDAR, these big, beautiful channels of glacial outwash. And Bingham Creek's way too small to have created these. All right, I wanted to also acknowledge, a lot of the incredible work by many of my coworkers at the Geological Survey, along with other geologists in the Pacific Northwest. This is an image of the Nisqually River in the southern Puget lowland. And this is a geology map of that same area. So a few years ago, my colleague Michael Pollins and others mapped this area. We'll go out to the full map here. I'm lucky because I get to draw from a lot of the knowledge and the information that, all the geologists that I get to work with get to collect. And I learn from them every day. So I just wanted to throw that in there. All right, let's zoom back out to the full Puget Sound view. This is a U.S. Coast survey chart from 1867, which includes depth soundings. We'll zoom in a bit here to our neck of the woods. And you can see there's just a ton of great information, about the bathymetry of Puget Sound and what's going on underneath the water. So sometimes it's informative to see what's going on the bottom of the ocean and the land. So here's what that looks like today. We have a little bit better information. Zoom out a little bit here. So if you were here and caught Ralph Haggerud's talk last year, well, let's add some land in here first. We can look up here and notice that little line there. That is a glacial moraine, and that's a glacial moraine. So we can see a lot of those ice extents even from the data that's coming from underwater, which is pretty neat. We're going to zoom into this area on Whidbey Islands, right where that glacier met the land, and get a little bit closer view. So there's all sorts of fun things happening in this image. There are these glacial lineations right here. There are these kettle holes, this kettle-like landscape over here. There's even dunes flowing up here. I was looking across from Port Townsend this afternoon, basically right at this bluff. So kind of neat to be so close to such interesting features. But if we change this to a colorized view, we can see some other features. And this is a glacial outwash delta. So is this, you see all these little channels flowing off of here. This is basically at the edge of the glacier where water was flowing off, dropping sediment, creating these big deltas. And it's a good spot to build an airstrip too. You can see the Coupeville naval, I think it's naval airstrip right there. Nice flat spot for landing an airplane. All right, let's zoom over to Fort Erie State Park. So this is just to the west. And Fort Erie is a beautiful forested state park, got a nice view of the strait. If we look at the LiDAR though, we can see that there's definitely a glacial story happening here as well. And, you can see this hummocky underlying landscape where the Puget lobe dropped off chunks of ice and formed these depressions as sediment flowed around that melting ice. So just want to note lake, is it Pondilla or Pondia? Anybody know? We'll call it Pondia, sure. I think this is with the largest kettle over there. Here's a nice view from the air of that kettle. It's nice to get the scale of these nice big houses next to the even larger lake. All right, moving back over to Port Townsend, I found this really neat, even older map from the US Coast Survey of the region. And, it's a pretty recognizable landscape where we are up here. The one interesting thing I noticed, though, is Portage Canal, which I guess I didn't really realize was not a natural canal. And it's called portage because you used to have to portage over top of this spit. So it's kind of neat to see that represented in this older map. But let's zoom into Port Townsend. Pretty much looks the same, right? Point Wilson, Point Hudson, pretty much in the same spot. Here's the LiDAR view. They did a pretty good job. We'll zoom back out to the Fuller Quimper Peninsula. And you can start to see those interesting patterns on the land. Let's zoom in over here. I see some interesting things happening. So these little snake-like features are called eskers, and those are basically areas where there was a subglacial tunnel underneath the ice. The water was flowing, dropping sediment that created these ridge lines. And this is another really interesting feature flowing across here too, this sort of ancient channel. I don't think there's any modern day river flowing through there. Here's a photo view. I don't know, maybe somebody lives there and could tell me if there is or not. That was Chimacum Creek? So this is over right there. Let's just move over a little bit. Coming close to the end of the presentation here, but this is the Elwha Delta over here, Tongue Point, Lake Crescent. You're familiar with those landmarks. But this is one of my favorite images because when you peel away those trees, you can just see the ice scraping across the land. Truly amazing. All right, so we've got all these different glacial landforms all over the place. There's many I didn't show tonight. Several years back, I was like, well, let's make a map of the Puget lowland that shows some of these and features some of these. So there's the aerial view of Puget Sound. And the blue is representing basically everywhere that ice was during the maximum glacial extent. And then here's the map that resulted. If we zoom in, we can just see different things featured. I brought a bunch of these with me tonight. If there's still any left back there, definitely feel free to grab one. It's fun just to spend an hour looking over all the interesting landscapes of our region. With that said, there's more than just glacial features here in Washington. And I just started on a project with a couple of colleagues of mine at the Geological Survey to make a geomorphology atlas of Washington that features Lidar sort of as the driver for showing a lot of these different features. So maybe we'll get to come back and talk about that in a few years' time. But this is something I love to do, so hopefully it was interesting to everyone here tonight. Obligatory data slide. That's all I got. I promise I'll stop hurting your ears. Thank you. I'm happy to take any questions. Maybe I can use that microphone. So the question was about whether the underwater features is coming from LiDAR data or a different source, and it's mostly sonar for the underwater features. There is a type of LiDAR called green LiDAR that can detect landforms underwater only to a certain depth. Usually it's only a few meters if it's very clear water, but yeah, usually that's a different kind of technology for the bathymetry. Yeah. Yes.
About 2/3 of the way through your slides, you showed the separation between Marrowstone and Indian Island, and it looked, there were 2 or 3 shots, it looked as though it was solid, and yet I understand 100 years ago that was open. Do you recall?
Go back here. So the question was whether it's solid between Indian Island and Marrowstone Island right here. That's probably just more artifact of the scale and resolution that I'm showing this at. I think that shoreline is based on low tide too, so that probably might make it appear a little more solid than it really is. Oh, sorry. Any other questions? I appreciate everyone being here and listening. Thank you so much. Oh.
Looking at your pictures of the glacial moraines, for as quite of information, I've been locating concentrations of various species of flounder, sole, and halibut, and are all sitting on those moraines. They like that. You leave the moraine, they eat there.
That's funny. I got something to say to that. I don't know if, a friend of mine told me that this is a really great fishing spot right out here. So that tracks really well for sure. It's connections to geology and everything, right? Any other questions?
Have you been hired and fired?
Oh. The question was, have I been hired and fired? Not yet, fortunately. Time will tell, I guess, right? I don't work for the Fed, so I'm a little bit safer, marginally. Someone have a question? Yeah.
I don't know how to put this, but there was a part
Right into the microphone.
There was a place where there was a lot of what is now certainly sea water, and it seemed like it was close to an area that you were describing as ice. And I'm wondering about whether the salt in the ocean, or was there less salinity at that time? Or,
I'm not sure.
Yeah, I'm not saying it.
That's okay.
But there was a place there that it seemed like there was a lot of ice features and seawater very close proximity. I was wondering about the branch.
Yeah, I'm not sure. I might have to see which.
Yeah.
Maybe we can go through them afterwards. Yes.
So clearly LiDAR has transformed the ability to see the landscape. But I just wondered, what do you think is next? Is there something that would go beyond LiDAR, that something would add to LiDAR that would give us new capabilities?
That's a good question.
Can you repeat it?
Yes. The question was, what's next beyond LiDAR, whether there's something that can give us more capabilities in the future. That's a really good question that I don't think I really have the answer to. There's VR technology I think it may be the communication and understanding part of geology. There's going to be new opportunities probably. LiDAR is getting more and more detailed, so it's not different than LiDAR, but we're having a hard time keeping up with just storing it because it's getting larger and more detailed as time goes on. So yeah, I don't know. That's a good one. I need my crystal ball for that one.
Big enough MRI would look into the rock.
There you go. Yeah, we might all be in trouble if we were surrounded by a giant MRI. Yes.
This might not be a welcome question, but have you seen anybody trying to take data sets through artificial intelligence where they've identified different parts of the landscape in certain geological things and let the computer take over classify things?
The question was about artificial technology using LiDAR to identify certain geologic features and things. And I haven't seen that, though I'm sure there's somebody doing it right now. Most likely. Yeah. Yeah. If you've thought of it, somebody's doing it probably. Good or bad or otherwise. Oh, I could.
So thank you to Daniel. You do such excellent work.
Thank you.
Breathtaking. You had an image on one of your early slides. It was a slide that had a whole bunch of different maps on it. And in the bottom right, you could see white with some peaks sticking through it. Does that ring a bell? If not, I can look.
It does, but we can look. Yeah. Yes.
For a lot of the images you showed coming from the 1 meter resolution tiles that are available publicly.
Yes.
Of the Straits and Puget Sound.
Yes.
And then for the Olympic Mountains, were you just using the 5 meter, or did you come up? I've been trying to mosaic all of the LiDAR data in Olympic Mountains, and that is challenging because of the way they were done.
Yeah. So the question was about the data resolution. I'm mostly using the 1 meter data. There's some places that have sort of older, coarser data sets. The Olympics were one of them. They got reflown last year, so there's newer data there. I should have shown a map of the Washington LiDAR portal. All of this data is publicly available for anybody to use. It's a little tricky to access it, and it takes up a lot of space. So, but if you just Google Washington LiDAR portal, that will come up. And we now have LiDAR coverage for the entire state. There are 2 areas on our website where we don't have data, and that's the Colville Reservation and the Yakima Reservation. The data exists; they just control that. So you got to get a hold of them to use it. But everywhere else, we have information for. So it's getting easier to put things together. But LiDAR is really expensive to collect. So historically, there was a patch here, a patch there, depending on who was interested in it. And now it's all filled in. So it's getting a lot better. Yeah.
One more round of applause.